The wing part suspected of belonging to that missing Malaysian Airlines jet is now in a lab for analysis.
Officials are increasingly sure this is part of the fatal Malaysian Airlines plane that disappeared 16 months ago without a trace.
At 12:41 in the morning on March 8, 2014, a Boeing 777 lifted off from Kuala Lumpur International Airport. It carried 239 people, 227 passengers, and 12 crew, bound for Beijing on what should have been a 6-hour flight, so routine that most passengers had probably fallen asleep before the Malaysian coastline disappeared below the clouds. 40 minutes later, the plane was gone. Not missing, not delayed. Gone as in no signal, no distress call, no wreckage, no explanation. Just silence, where an aircraft the size of a building used to be. For more than a decade since that night, governments have spent over $200 million, deployed submarines, satellite networks, sonar fleets, and autonomous deep-sea robots across more than 120,000 square kilometers of ocean floor, roughly the size of Pennsylvania, and found almost nothing. A handful of debris fragments washing up on beaches thousands of miles away in Réunion Island, Mozambique, and Madagascar. No cockpit voice recorder, no flight data recorder, no definitive crash site. The disappearance of Malaysia Airlines Flight MH370 has been called the greatest aviation mystery of the modern era. And for good reason. In an age when a smartphone can be tracked to within a few meters and satellites photograph individual cars from orbit, we somehow managed to lose a 200-ton jet aircraft and couldn't find it for over 10 years. That's not just embarrassing, it's haunting. And for the families of those 239 people, many of whom still hold vigils, still refuse to accept official pronouncements, still demand answers. It has been a decade of grief, with no grave to stand at, no closure to hold on to. But in the middle of that long, painful silence, a retired British aerospace engineer named Richard Godfrey sat down at his desk, reportedly working voluntarily, 8 hours a day for years, and decided to try something that sounded, frankly, ridiculous. He was going to track a missing aircraft using the faint whispers of amateur radio hobbyists. And the scientific community is now taking him very seriously. Before we get to Godfrey's method, we need to understand the official story, and more importantly, we need to understand why so many aviation experts believe the official story was wrong. Here is what investigators have told us, in broad terms. After the transponder went dark at 1:21 a.m., Malaysia's military radar, which works differently from civilian air traffic radar, bouncing a signal off aircraft and catching its reflection, tracked an unidentified blip, making a deliberate, controlled U-turn. This was, investigators later concluded, almost certainly MH370. The aircraft had swung back west, crossing over the Malay Peninsula, and disappeared northwest of Penang Island at around 2:22 a.m. From there, the only evidence came from a series of automatic satellite handshakes, 7 so-called pings, that the aircraft's onboard satellite data unit exchanged with an Inmarsat satellite over the Indian Ocean. These weren't communication signals. They were maintenance handshakes, a system check, a quiet, "I'm still here" signal that the plane sends automatically. Engineers analyzed 2 key data points from each ping: the burst timing offset, which measures the delay in the signal's round trip, and the burst frequency offset, which captures a tiny Doppler shift caused by the plane's movement. From this data, investigators derived enormous arcs stretching across the globe, lines along which the aircraft could theoretically have been at the time of each ping. The northern route was ruled out. Too many radars, too many military assets, too many countries for rogue Boeing 777 to have gone unnoticed. So the southern arc became the focus, leading to what investigators called the 7th arc, the line corresponding to the final ping at 8:19 a.m., the moment they believed MH370 had run out of fuel. Everything else, the search zones, the hundreds of millions of dollars, the fleets of ships, was built on that arc. And yet they found nothing, which raises an uncomfortable question. What if the arc was right, but the assumptions built on top of it were wrong? Because the arc itself is not a location. It is a line, a sweeping curve across the Indian Ocean, hundreds of kilometers wide. To narrow the search to a specific zone, investigators had to layer assumption upon assumption. That the autopilot was engaged, that the fuel burn matched standard models, that the aircraft flew in a straight line, that no one was in the cockpit making adjustments during that final phase of flight, and the debris that did wash ashore told a troubling story. The flaperon recovered on Réunion Island in July 2015, confirmed by French aviation authorities to be from MH370, showed signs of what investigators described as flutter damage, the kind of violent, high-speed structural failure that occurs when a control surface shakes uncontrollably in fast-moving air. The flaps on that piece were retracted, meaning the plane was in cruise configuration, not set up for any kind of landing attempt. A wing flap section found in Tanzania showed fracture patterns consistent with what the Australian Transport Safety Bureau described as high-energy, high-velocity impact, not a controlled glide. And perhaps most critically, the burst frequency offset data from that final 8:19 a.m. ping suggested the aircraft was descending at potentially 15,000 feet per minute in its final moments, according to the ATSB's own 2016 review. That is not a fuel-exhausted glide. That is a nosedive. So the wreckage says high-speed impact. The final data says steep descent. And the search that covered 120,000 square kilometers of seabed found nothing. The logical conclusion, for an increasing number of aviation analysts, is that they were looking in the wrong place. Richard Godfrey is not a professional investigator. He is not affiliated with any government agency or airline authority. He is a retired British aerospace engineer who, by his own account, worked on the MH370 case voluntarily, 8 hours a day, for years. That kind of obsession either produces breakthroughs or breakdowns. In Godfrey's case, it may have produced one of the most compelling new leads in the history of this mystery. His idea centered on a technology called WSPR, Weak Signal Propagation Reporter, pronounced WSPR. It is a system developed in the early 2000s by Nobel Prize-winning physicist Joe Taylor at Princeton. Its original purpose had nothing to do with aircraft tracking. It was designed for amateur radio enthusiasts, ham radio operators, who wanted to test how far their signals could travel. Here's how it works. Thousands of amateur radio stations around the world, operating on minimal power, transmit short, precisely timed radio signals every 2 minutes. These signals are extraordinarily weak, often less than a single watt of power, roughly equivalent to a night light, but because they bounce off the ionosphere, the upper layer of the atmosphere, they can travel extraordinary distances. A station in South Africa can pick up a signal from a station in New Zealand. The data from each exchange, timing, frequency, signal strength, gets automatically logged to a publicly accessible online database called WSPRNet. WSPRNet contains, at this point, billions of log data points stretching back years, an enormous, globally distributed record of radio activity, quietly accumulated by hobbyists with no thought that anyone would ever use it for anything beyond testing antenna designs. Godfrey had a different thought. When a large aircraft, say, a Boeing 777, flies through the path of one of these radio signals, it disturbs it. It might cause a tiny dip in signal strength, a faint shift in frequency, an anomaly small enough that no individual radio operator would ever notice it, but significant enough to show up in the data if you knew what to look for. He called these disturbances anomalies. And he hypothesized that if MH370 had flown across the Indian Ocean on the night of March 7th to 8th, 2014, it would have sliced through dozens of these invisible WSPR threads and left a trail of disturbances in the WSPRNet database. The database goes back far enough to include that night. The data was sitting there. No one had looked at it this way. So Godfrey looked. What followed was not a weekend project. According to Godfrey's own documentation on his website, MH370search.com, the work stretched across years and involved analyzing more than 200 billion lines of raw data from the WSPRNet archive. He developed custom software to filter out interference from solar activity, atmospheric disturbances, and normal background noise. He focused specifically on signals in the 14 MHz frequency range, which reacts in a predictable, well-understood way when a large metallic object, like a Boeing 777, passes through it. He set a threshold. Only anomalies measuring approximately negative 25 decibels or stronger would make the cut. Everything else was discarded. What he was left with, for the night of March 7th to 8th, 2014, was approximately 130 anomalous whisper signals over the Indian Ocean, and when he plotted them in chronological order on a map, they formed a track. The track began at a location consistent with where Malaysian military radar had last detected the aircraft northwest of Penang. It curved southwest, then turned south, and it ended at a specific set of coordinates: 29.128 degrees south latitude, 99.934 degrees east longitude, approximately 1,560 kilometers west of Perth, Australia. As Godfrey himself stated, quoted in Malay Mail, the MH370 crash location, defined by the Whisper technology, is within a circle with a radius of 30 kilometers and centered at 29.128 degrees south, 99.934 degrees east. Critically, this was an area no official or private search had ever examined. The major Australia-led search had focused on a different section of the 7th Arc Ocean Infinity's 2018 campaign, had concentrated its efforts in another corridor. Godfrey's coordinates sat in a gap between them. To validate his work, Godfrey submitted his methodology and findings for independent analysis. The University of Liverpool examined his data using Bayesian statistical analysis, the same probabilistic method that had been used to help locate Air France Flight 447 after it disappeared in the Atlantic in 2009. According to reporting by Airline Ratings, the analysis returned a 74% probability that MH370's wreckage lies within a defined area centered on Godfrey's coordinates. Additionally, Godfrey's team conducted a real-world validation test. They chartered a Boeing 777 and flew it along the Indian Ocean corridor consistent with the suspected MH370 route, while Whisper stations monitored the network in real time. According to Godfrey's published documentation, the Whisper anomalies appeared precisely when and where the test aircraft was flying. Not approximately, not vaguely, but with timing that matched the aircraft's position to within minutes. The method was not theoretical anymore. It had been demonstrated to work. One of the most compelling aspects of Godfrey's case is not the Whisper data alone. It is how multiple independent lines of evidence converge on the same geographic area. Consider the debris drift analysis. After the Flaperon was recovered on Réunion Island in 2015, and other MH370, linked debris appeared on coastlines in Mozambique, Madagascar, and Tanzania over the following years. Oceanographers at the GMR Helmholtz Center for Ocean Research in Kiel, Germany, conducted extensive drift modeling. They ran hundreds of thousands of computer simulations, releasing virtual trackers into digital models of Indian Ocean currents and tracking where they washed ashore over time. When they reverse-engineered those simulations, tracing the debris paths backward from where they arrived to where they originated, the majority of trajectories pointed to an origin zone within approximately 100 kilometers of Godfrey's coordinates. That is a remarkable degree of independent convergence. One method uses radio signals recorded by amateur enthusiasts. Another uses oceanographic current modeling with simulations run by a German research institute, and they point to the same patch of ocean. Then there is the flight simulator data. In April 2024, Godfrey published analysis on his website, noting that flight path data recovered from Captain Zahari Ahmad Shah's home flight simulator, which had been examined as part of the original investigation, showed a simulated route passing directly through the Whisper-derived crash location. This is not conclusive evidence of intent. Simulator data can be ambiguous, and the captain was never formally charged with any wrongdoing by investigators. But it is another thread, from another entirely independent source, that runs through the same coordinates. And there is the Inmarsat data itself. Godfrey's 130 Whisper anomalies all fell within approximately 4 minutes of the known Inmarsat satellite pings. In other words, every time the satellite recorded a handshake with MH370, there was a corresponding Whisper disturbance in the same region. Not sometimes, not mostly, every time. In his most recent published analysis as of early 2025, Godfrey refined his crash coordinates further, citing a candidate location at 29.178850 degrees south, 99.85352 degrees east, approximately 39 nautical miles southeast of the 7th Arc. His analysis notes that this is the only location that simultaneously satisfies the Inmarsat BTO data. the BFO data, Boeing 777 performance parameters for speed and fuel endurance, and the pattern of whisper anomalies along the flight path. It would be dishonest to present Godfrey's work without engaging seriously with the critics. Science demands scrutiny, and this case has had plenty of it. The most significant technical objection comes from the whisper methodology itself. Joe Taylor, the Nobel laureate who invented the system, has publicly stated that while aircraft can indeed disturb whisper signals, using those disturbances to pinpoint specific locations is a significantly harder problem. The signals can be disrupted by dozens of variables: solar events, atmospheric irregularities, ionospheric layers shifting with temperature, and distinguishing a genuine aircraft signature from natural noise requires extremely careful filtering. Jeff Wise, a journalist and aviation analyst who has followed the MH370 case closely and maintains a critical newsletter on the subject, has raised a concern that Godfrey's successive revisions to his crash location, from approximately 33 degrees south in his initial 2021 work to 34 degrees and ultimately to 29 degrees south, suggest a methodology that may be reactive rather than predictive. Wise has characterized the shifts as each revision being reactive, not predictive, questioning whether the model is being adjusted to match known outcomes rather than deriving new predictions from fixed inputs. This is a legitimate scientific concern. A model that keeps changing its answer as more context becomes available can mean one of two things. Either the data is genuinely improving and the refinement is appropriate, or the conclusions are being reverse-engineered from the desired result. Godfrey's response, and the response of independent analysts who support his work, is that the refinements reflect improvements in data quality and algorithmic processing, not adjustments to match search results. They note that for over 14 consecutive months, his target coordinates have not shifted. That stability, they argue, is exactly what you would expect from a model that has converged on the right answer. The debate is real and unresolved. What is not debated is the basic physics. Large metal aircraft do disturb radio signals, and those disturbances are loggable. The question is whether the disturbances in the archive are recoverable with sufficient precision to locate a specific aircraft. Godfrey's real-world flight test suggests yes. Critics remain cautious. By late 2024, the conversation around Godfrey's work had moved beyond academic debate. Governments were listening. In December 2024, Malaysian Transport Minister Anthony Lok announced that the Malaysian cabinet had agreed in principle to a new search proposal from Ocean Infinity, a marine robotics company that had previously led the 2018 search campaign. The new search zone was to cover 15,000 square kilometers of seabed in the southern Indian Ocean, centered on an area identified through updated data analysis, including the whisper-derived coordinates. The contract was structured on a no-find, no-fee basis. Ocean Infinity would fund the entire operation, estimated at approximately $70 million, and would only be paid if the primary wreckage was successfully located. Malaysian officials confirmed the agreement was formally signed in March 2025. Ocean Infinity deployed their vessel Armada 7806, equipped with multiple Hugin autonomous underwater vehicles, robotic submarines built by Kongsberg Maritime, capable of diving to 6,000 meters and operating untethered for up to 4 days, scanning the seabed with synthetic aperture sonar detailed enough to identify large structural objects. Phase 1 of the search began in late February 2025. A second phase launched on December 30th, 2025, using a different vessel, Armada 8605, with 3 Hugin AUVs. Between the two phases, Ocean Infinity surveyed approximately 7,571 square kilometers of seabed, a substantial but incomplete portion of the 15,000 square kilometer search zone. In March 2026, Malaysia's Air Accident Investigation Bureau confirmed what many had feared. No confirmed MH370 wreckage was found. The Bureau's statement was precise and important in its wording. The search activities undertaken have not yielded any findings that confirm the location of the aircraft wreckage. This is not the same as saying the aircraft is not there. It means the surveyed area, which, crucially, did not cover the full contracted zone, produced no detection. Weather in the southern Indian Ocean proved a significant obstacle, periodically halting operations. The targeted region includes some of the most challenging underwater topography on Earth. deep volcanic ridges, seamounts, and abyssal trenches that complicate both navigation and sonar imaging. And so, in July 2026, Malaysia formally extended its contract with Ocean Infinity for an additional 12 months, running through June 2027. Transport Minister Anthony Loke confirmed the extension covers the remaining approximately 7,428 square kilometers of unsearched territory within the contracted zone, the areas that weather and operational constraints prevented the earlier phases from reaching. The no find, no fee terms remain in place. The search is not over. It is easy to focus on MH370 as a puzzle, a thrilling, maddening mystery that rewards armchair investigation and generates compelling content. But it is important not to lose sight of what this search actually